A few months ago, I made some super concentrated nitric acid, which was close to 100%. My main purpose with that video was to explore some of its different properties, and of course, to also show that it could light common lab gloves on fire. So when working with it, you either need to use a different type of glove that's chemically resistant, or to just wear none at all. At the end of the video, I did a small demo where I added it to kerosene, and I showed how it made it burn a lot better. I also briefly mentioned that this mixture of nitric acid and a fuel is commonly used in liquid-propelled rockets. However, at the time, I really didn't know much about rockets in general, so I didn't go into any real detail. After posting that video though, I got a lot of comments encouraging me to explore liquid rockets in general. A patron of mine was even kind enough to send me a book called Ignition by John Clark. I initially planned to just read the book for fun, but by the time that I was about halfway through it, I knew I had to try out some of it for myself. However, the book was very clear about how dangerous this could be, so I was careful to only choose the reactions that I felt comfortable with. When it comes to liquid rockets, most of them are based on a bipropellant system where a fuel and an oxidizer are reacted together to generate the thrust. These are some of the common bipropellant mixtures, and they generally fall under two main categories, hypergolic and non-hypergolic. The non-hypergolic ones need an outside ignition source to get the reaction going, but the hypergolic ones react so vigorously with each other that they self-ignite on contact. On a small scale, most of the non-hypergolic combos require a somewhat complicated setup to fire. Mixing the fuel and the oxidizer in the right ratio can be really hard, and it also requires an outside ignition source. I've never seen it done on lab scale, and this is what the typical professional setup seems to look like. On the other hand, for the hypergolics, I just need to mix together the two liquids, and it can even be done in a test tube. Periodic Videos has already covered this topic a little, and this was a cool clip from one of their videos. They had this cool setup where they filled two containers with a fuel and an oxidizer, and then they let them mix together. I might try something like this when I get a bit more comfortable with how this all works, but for now, I'm just going to be sticking with test tubes. An oxidizer that's commonly used is pure nitric acid, and I had some on hand from the previous project that I mentioned before. For the fuel, there were many options, but I just went with aniline because again, I already had it. Aniline was tried early on as a rocket fuel, but it was never really used, mostly because of its freezing point. In its pure form, it freezes at -6°C, which meant that it could only be used in warm climates. People tried to mix it with other fuels to lower this freezing point, but no one was ever really successful. The main fuels that are used now are hydrazine and hydrazine derivatives, but hypergolically, aniline should give a similar result. So, as I said before, the setup is pretty simple. All I needed was a test tube and a small amount of the nitric acid and the aniline. I started by adding the nitric acid to the tube, and then I dropwise added the aniline. There was a slight popping sound the moment it touched the acid, and it made me flinch a bit. It never ended up firing, but there was clearly a reaction going on that was causing the aniline and the nitric acid to boil. I decided to try it again, but this time I added a lot more aniline. Initially, it was just like before and it just caused it to boil, but then it suddenly ignited. After these two runs, I was getting a bit more comfortable with this mixture. So I decided to just shoot in a bunch of the aniline all at once. The reaction seemed to be quite fast though, and I felt that it would start igniting before I was even able to add all the aniline. To get around this, I shot it at the wall of the tube instead of directly into the acid. I was honestly a bit nervous to do this, but the result was definitely worth it. There was also a second firing, which was kind of interesting. I waited for the tube to cool and for all the gases to go away, and then I broke up all the solid stuff. I'm not 100% sure what this is, but I imagine it's a nice combination of carbon and a bunch of side products. I think that most of the aniline, though, was converted to gases like steam, CO2, nitrogen, and nitrogen oxides. In full-sized rockets, this residue can also form, and it can cause the combustion chamber to get jammed up. I think the amount that was formed here was excessive, though, because my ratio of aniline to nitric acid was definitely not ideal. Also, a real rocket maintains a much higher temperature, which helps burn everything away. I decided to try it again with a bit more of the two components, and the result was quite similar. The initial delay before firing seemed to be a bit smaller, but I think this was just because my first run used very little of both chemicals. The next thing I wanted to see was how it behaved in a smaller tube. This other one was both a lot shorter and thinner. The first thing that I noticed was that it seemed to have a smaller ignition delay. So on the computer, I went through the footage frame by frame to see if this were the case. What I found was that on average, the smaller tubes took about 12 frames from the moment of contact, and the larger ones took about 20. Considering that there's a 17 millisecond gap between each frame, this means that on average, the larger tubes took about 136 milliseconds longer to fire. I think the reason for this was the initial expansion of gas, which caused the liquid in the small tubes to mix a lot more violently. I don't know the exact reason for this, but I imagine it just came down to space, where the larger tube had a lot more of it to accommodate the expanding gas. In any case though, I think the ultimate effect of this was a more vigorous mixing of the liquids and a faster ignition. If you listen closely in the larger runs, there's a very distinct boiling sound as the vapor builds up, followed by a nice pop. But in the smaller tubes, it seems to happen way faster, and all the sounds just get jumbled together. And the last thing that I noticed was that when I slowed things down, the ignition point for the smaller tubes seemed to be consistently higher than the big ones. I think this makes sense with what I've found so far, and the more vigorous reaction is able to push the gases further before they ignite. However, because the smaller tube was so much shorter, the ignition happened really close to the end of it. After noticing this, my friend suggested shortening the tube even more to see what would happen. So I got out my Dremel and I cut off about a quarter of it. The first attempt kind of worked, but a lot of the contents were just thrown out of the tube. All the streaks of white smoke are from drops of nitric acid falling back down. The second try was really interesting, and I think it only just barely ignited. And when I went frame by frame, I was really intrigued by what I saw. The fire started way up in the vapor cloud, and then it traveled up to light the rest of the vapor and down to the liquid mixture. The third run was the best out of all of them. It ignited just barely outside the tube, and it gave a really nice sound as well. We figured that the length was probably close to the limit, but we wanted to see what would happen if it were even shorter. So I got out the Dremel again, and I cut some tubes in half. The first run was a total failure, and everything was just thrown from the tube. You can even see some aniline and nitric acid splattered on the back wall. The next one was also a failure, and it was again just a puff of smoke. For the last one though, I tried adding a lot less aniline, and I actually got it to ignite. From these tests, I couldn't really conclude very much, but tube length was obviously affecting ignition. I think the major reason was all the splashing that I mentioned earlier, and when the tube was too short, it just ejected everything before it got to the ignition point. Because I knew that the larger tubes didn't splash as much, I figured that at the same length, they should still be able to fire. So I cut them down and tried it a few times, and every time I was consistently able to get it to ignite. I also didn't need to use less aniline, and I just blasted it in like I normally would. After doing all of this, I was starting to get a feel for how this reaction behaved, and I felt comfortable trying one last thing. This is a photo of what a typical rocket engine looks like on the inside. Notice how the combustion chamber is more or less cylindrical, just like the test tubes. However, it then quickly gets more narrow before opening up to the nozzle. The general name for this is a convergent divergent nozzle, or a de Laval nozzle. I don't want to get much into the physics of it, but the overall idea is that it converts the thermal energy of the expanding gases into kinetic energy. The gas is forced through this thinner area called the throat, which greatly increases its velocity. In most cases, the gas before the throat is moving at subsonic speeds, but afterwards, it can be going as fast as 10 times the speed of sound. After the throat, the gas expands, and as it does so, it pushes on the nozzle. There's also a strong pushing force at the back of the combustion chamber, and together, this is what makes the rocket move. I wanted to see if I could kind of mimic this with a test tube, but of course I was a little bit hesitant because I didn't want it to explode. I heated them using a torch, and then I stretched them out to try to mimic the throat. The larger tubes were a lot thicker, so I was more comfortable starting with them. For the first run, I used the one with the least narrow neck. The result was almost the same as the unnarrowed tube, but it gave me the confidence to push it a bit further. The biggest difference for this one was definitely the initial pop that it made. I don't think the microphone was able to pick it up very well, but it was significantly louder. I did a couple more runs of this to build my courage, and then I moved on to the smaller ones. The glass in the smaller tubes were a lot thinner, and there also wasn't nearly as much space to accommodate the gas expansion. This meant that not only were they weaker, they'd probably have to withstand a higher pressure, which meant they might break. Just like before, I built it up slowly, and I started with one that was only narrowed a bit. Then I nervously tried a much thinner one, and it was a complete failure. Not only did I spray the back wall with aniline, but it never fired. However, I still thought that it kind of ended up being interesting. I decided to try it again, and for the next 2 runs, it still didn't fire. The reason for this seemed to be similar to before, where it was splashing way too much and stuff was getting ejected from the top. From my earlier test with the shorter tube, I saw that adding less aniline could still get it to fire, so I decided to try that here. I also shot it more directly into the side of the tube so that it wouldn't just be blasted into the acid. This time it actually worked, and the tube also didn't explode, so I decided to try it 3 more times with a thinner throat. Anyway, for me, this project was just an introduction to the whole world of liquid-propelled rockets. I definitely plan to explore more rocketry in general, and I think for the next one, I'll look into some of the other hypergolic oxidizers and fuels. However, I'm not exactly sure when I'll be able to do that, because I've been having a lot of trouble getting my hands on the hydrazine-based fuels. In the end, I'll make them if I have to, but if any of you guys know a source that I can get it from, please send me an email.